Now let's talk about problems with 3D geovisualizations. So the most important one here is the scale variation across 3D things. Okay, so in summary, it means that when most people, when we're looking at a fake 3D environment, I'm calling it fake because your 2D screen is, after all, 2D, right? When you're looking at a 3D geovisualization, especially static ones, when you're looking at them, it's pretty hard to make correct judgment about size, about depth, or about distance. Okay, so it's pretty hard to solve this problem. It's not possible to completely solve it, but we do have methods. We do have methods, and these are methods. First one, reference frames. You add reference frames to your 3D geovisualization to give people some anchors or some baselines, okay, to help them perceive distance and shape, okay? Examples would be like this, right? So here we have a globe. It's a 3D globe, and there is nothing else. But if we add this red frame, it's actually a latitude, longitude grid, right? Around this globe, using it to wrap the globe, it's relatively easier for people to judge distance and size. Another one is this one. We have seen this visualization before. Here, what's the reference? The base map, the base reference map is what? Is the reference frame, right? We can see blocks, we can see roads on this 2D reference map. So this map will help us perceive distance and size. We do have other methods to implement the same thing, right? To help people make correct judgment on distance, on shapes. Here, say, yeah, it's called divided symbol stacks. It means that you use small gaps between the symbols in each stack, automatically adjusted by the software to remain proportional to the standard symbol height, okay? For example, here, so this is a very common thing when you are using ArcGIS, right? So here, for this example, the author tries to use 3D bars, vertical bars, to show the structure of population age, right? Different categories there for different people of different ages. So here you can say for each bar, there are multiple small cubes. Each one represents a specific category of age, and between them, there are boundaries. There are gray boundaries, right? So these boundaries, they separate small units to help people perceive the correct size, or you can say a correct length or distance of each small unit. Here specifically, each small unit is a cube on each bar, right? So that's another method here. So we can also use something called non-perspective projections to solve the problem, to solve people's misjudgment about distance. For example, in this 3D geovisualization, we have so many bars. And if you are looking at these bars closer to you, usually you should feel, I mean, this is for common people, for public, right? It's not impossible that you could be the special one. So for most people, you will feel that these bars, they're leaning to you, right? But for those bars away from you, you feel that they're leaning away from you. So this is the perception we have. And we don't want to have that because this visualization is just complex enough. People need to estimate, to perceive distance and shape correctly. Here is something called non-perspective projection or orthogonal projection. If you compare this geovisualization with this one, you will feel that all the bars in this geovisualization, they are all perpendicular to the surface. Even those bars very close to you, you do not feel that they're leaning to you, right? So projections, orthogonal or non-orthogonal, perspective or non-perspective. So the difference is here. Here is an example for orthographic projection. Here is perspective projection. So for orthographic or non-perspective projection, everything seems equal, no vantage point, and the parallel lines never touch. What is a vantage point? Here is an example. We have this railway. Obviously, there are two rails. It's pretty sure we're sure that they're parallel to each other in real world, right? But here we have a vantage point where these two parallel lines, they actually intersect in this photo. And this is not real, right? Because in real world, they should not do that. They should not interact. So orthographic or non-perspective projection will avoid this situation. But for perspective projections, they do have this problem, okay? So that's the difference. And orthogonal or non-perspective projections can partially solve the misjudgment of people on distance and shape. But again, I mean, it's for most people. It's for most people. It may not work on some special people, right? And next, let's talk about symbol occlusion problem. Most of 3D geovisualizations, or more broadly, visualizations still suffer from symbol occlusion. If we use another word, it's called symbol blocking. Symbol blocking. So there are multiple solutions for this, but before that, let's see this example. So here, obviously, this image, this picture was taken by a camera in the sky, and we see skyscrapers everywhere within this picture, and you see that some buildings, some skyscrapers, they are blocked by others. If you consider this as a geovisualization, some of them, they're blocked by others, right? So it's called symbol occlusion if you consider each building here as a symbol, right? So solutions. The first one is called object culling. It means that if, say, building A is blocking building B, if you want to say the situation, if you want to observe building B, you can just eliminate building A temporarily. Because currently, I don't want to say you, I can make you transparent, or for now, we don't render building A. So building B can be seen. And then if you zoom out, you want to say building A, you don't care about building B anymore. Say again, render building A. So here, this concept, object culling, is not only for geovisualization, it's a technology widely used in computer science and in 3D environment rendering. Here is an example. If you're interested in it, you should go inside and say how people implement object culling in 3D visualization. And next method is not that complex. Like it's not that complex as object culling. It's called object minimization. Reduce the size of less important objects. Say we want to say building B, but it's blocked by building A. Let's just make building A very small. Or reductions in both heights and the weights possible. Again, make it small. Weight reduction more useful when comparing heights of selected symbols with all other symbols in a scene. In summary, if something is not important, you don't want to say it for now, make it small. And we can also use other methods. For example, object displacement, right? If building B is important, building A is not, just raise building B. Okay, or move building A away from building B so it will not block building B, right? Or you can use view distortion, distort the geometry of a surface, right? The example we saw before, a fish eye view, which selectively distorts a scene so as to enlarge objects near the point of interest. here, right? For example, the building on the left here can be seen very clearly, but other buildings away from the camera, they cannot be seen very clearly. So obviously you are doing this distortion on purpose. I mean, the shape of this building has been distorted, but that's on purpose because you want to observe it closely and clearly. So that's another way to say to solve the problem. Well, the next we still have other methods for object occlusion problem. Next one is more complex though. If you can make your geovisualization, 3D geovisualization dynamic, it will be very convenient to solve this problem. I think that's a perfect way to do this, right? It's called rotation of viewer movement. So it means that when you're looking at a specific geovisualization, some buildings, some symbols, they're blocked by others. What if you can rotate this geovisualization? Then all those symbols you cannot say can be seen right now. Or if you cannot rotate the geovisualization, if you can change the direction of your view, you can look at the same geovisualization from another direction, then the problem is also solved. Okay, so another effect I want to introduce here is called kinetic depth effect. It means that when we're looking at a static geovisualization, 3D geovisualization, we have very poor judgment on distance and the spatial relationship among different objects in your geovisualization. But if you can rotate, if you can make your geovisualization move, then this dynamic will help you perceive the correct spatial relationship among different objects. Here is an example. Here is a static image of a forest, part of the forest. We'll see this type of image later in LiDAR, in the topic of LiDAR. We can see a lot of red and orange and yellow points here. They are the top of trees, okay? And their color is proportional to the distance between that specific point and the surface. So if the color is red or yellow, it means it's pretty high, right? If the color is blue or light green, say that, it means that the elevation, the distance between that point and the surface of the Earth is pretty short. The elevation is low. So here we can say a lot of trees, right? We have multiple canopies here, and the surface of the Earth is in blue in general. If we can make it move, sorry, this GIF here is not moving. I'm not sure why. I think it's PowerPoint, but I have listed the source here. If you want to see it move, go to this website. You should be able to download this LiDAR GIF. Let's get back. If this image can move and rotate, then you will have a better perception of the shape of those trees and the relationship, spatial relationship between trees and the ground. There will be this 3D effect instead of this still LiDAR image. If I did not tell you that these points are for surface and the canopies of trees, it's pretty hard for you to read that, to find out, okay, that's the truth. Okay, it's a forest. Okay, and I've mentioned before, I actually have mentioned this before, symbol transparency can also help with symbol occlusion, right? For example, here, still we have a lot of bars, but here we can see some of those green bars, they are half transparent. If they're transparent, then other red bars blocked by them can be seen partially. But again, this brings a lot of burden to your readers, because if you're making some symbols transparent, some not, this geovisualization is actually becoming more complex. your readers will be more careful when they're trying to get information. Okay. And the next one is not very usually used. It's called symbol shadows. It's usually used for spatial. We call it spatial temporal cube like this, or any 3D cube. Say that we have 3 axes, and you want to locate geographic and entities within this 3D environment. For example, here we have a lot of red points within this space. Obviously, they're blocking each other. Another method to solve this blocking is to project all of these red points to the surface, to a 2D surface like this. You can say we have black dots. They are forming a cloud on the surface, right? And they are the projections. These black dots, they are projections, vertical projections of these red dots. It's pretty easy, but the problem is that the spatial relationship of these red dots along the 3rd dimension, along the vertical axis, has been completely eliminated after projecting all of them to the 2D surface, because the 3rd axis just disappeared. So if the 3rd variable or 3rd axis is not very important to you in your geovisualization, you can do this. But if the 3rd axis or the variable who is using the 3rd axis is pretty important to your geovisualization, you don't want to do this, because when you are projecting everything to the surface, the 3rd variable will just disappear. Okay. And the next method, I mentioned this before in the data mining tools in the first topic, right? In the first topic of the class, geovisualization. We can also use multiple views to address the same 3D geovisualization, to look at the same area from different directions to get more information. So when we're using multiple views, something blocked in one of the views can be seen in another view or in other views, right? Here is a very simple example, right? The first view here is showing a specific building. The second view here is actually a blueprint, or you are looking at the same area from the right above. And the third view here is very typical for multiple linked views. It is looking, in this view, you are looking at the same building from another direction, from another perspective, right? So something, all those things have been blocked by this building in the first view. They can be seen in this view, right? Okay, I will just stop here. Let's just continue in the next video. Thank you.